Welcome to today's explainer. All right, middle school science class. I know exactly what you're thinking when you hear the word physics. You're probably picturing like giant heavy textbooks, endless chalkboards, and formulas that just put you right to sleep, right? Well, actually, scratch that. Today, we're totally flipping the script. We are going to reframe physics. It's not some boring stuff you have to memorize. It's literally a real-world superpower. It's kind of like the secret cheat code to understanding how the universe actually operates. And today, we're going to use that exact code to pull off something pretty incredible.
Okay, let's dive into this. Picture this. You're standing right next to this absolutely massive, towering skyscraper. Your mission, if you choose to accept it, is to figure out exactly how tall this building is. But here's the catch. You don't have a giant tape measure, you don't have some high-tech laser, and you definitely don't have a drone to just fly up to the roof. Literally, all you have in your pocket is a tiny rock and a basic stopwatch. That's the whole shebang. So, could you do it? Well, with your new physics superpower, yeah, you absolutely can. To solve this little detective story, we need to bring out our scientific magnifying glass. It's this simple, almost magic-looking formula. H equals 4.9 times t squared. So what does this actually mean? Well, in plain English, the height of the building in meters equals 4.9 times the amount of time the rock falls in seconds multiplied by itself. Squared. And this isn't just some random string of numbers and letters. No way. This comes straight from Sir Isaac Newton's laws of motion. It tells us precisely how far an object falls when it's grabbed by the invisible, powerful pull of gravity. Now you might be wondering, okay, where on earth does that highly specific number 4.9 actually come from? Well, it all comes down to gravity, which we represent with the number 9.8. Down here on Earth, gravity acts like this giant invisible magnet, just pulling everything downward. As an object falls, gravity accelerates it at about 9.8 meters per second every single second. It just keeps speeding up. And that 4.9 in our magic equation, it's exactly half of that earthly constant. It's literally baked right into the math. So let's put this into action, shall we? Imagine you've just taken the elevator all the way up to the roof of that skyscraper. Here is your specific step-by-step procedure. Step 1. You carefully, very carefully, hold your small rock over the edge. Step 2. The exact fraction of a second you let go of that rock, boom, you click Start on your stopwatch. And Step 3, you watch it fall, down, 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 and the literal millisecond you hear or see it smack the pavement, you click Stop on the timer. It definitely requires some sharp eyes and quick reflexes.
Okay, let's run the math. Let's say your stopwatch reads exactly 3 seconds from release to impact. We just plug that right into our Newton equation. So 3 seconds squared, which is just 3 times 3, gives us 9. Then we take our gravity number, 4.9, and multiply it by that 9. The result? 44.1. Just by dropping a tiny pebble and counting to 3, you mathematically proved the building is exactly 44.1 meters tall. You didn't even have to leave the roof. I mean, come on, that is the superpower of physics in action right there.
But hold on just a second. We've got our height, but as junior scientists, we've kind of hit a speed bump. I have a really critical question for you. Why do real scientists practically never trust just a single measurement? Think about it. If a biologist or a chemist does an experiment just one time, they don't instantly run out and publish a book about it. Why? Well, because we're human. Maybe your thumb just slipped a little on the stopwatch, or maybe you started the timer a millisecond late. We call this human reaction error, and it happens to the best of us. Now, what's really interesting about this slide is how we solve that pesky human error problem. We chart multiple measurements. Instead of just doing one drop and calling it a day, we record 3 distinct drops. We drop a second rock, and this time we clock it at 2.9 seconds. We drop a third and get 3.1 seconds. By charting this data out like this, we can instantly see the natural variations in our own reaction times. It wasn't exactly 3 seconds every single time, was it?
So, to get to the absolute truth, we calculate the height for all 3 of those measurements and just take the average. Think of it kind of like asking your friends for a movie review. If you ask just one friend if a new movie is good, you're only getting their single, maybe slightly biased opinion. But if you ask 10 friends and average their ratings together, you're going to get a highly reliable review. Calculating the average of our rock drops does the exact same thing. It smooths out those tiny human reaction errors and hands us a rock-solid, mathematically reliable result. This is exactly how the pros improve their data.
All right, before we take our newly discovered superpower out into the real world, we've got to tackle a classic trick question. This is one that literally fools adults all the time. Ready? Does a heavy rock fall faster than a light rock? Like if I hold a tiny pebble in one hand and a massive heavy boulder in the other, and drop them from the same roof, which one hits the ground first? Common sense might tell you the heavy one crashes down faster just because it weighs more, right? Let's see what physics has to say about that.
Well, whether you drop a heavy boulder or a light little pebble, the answer is exactly the same. They both fall at the exact same rate. No way, right? But it's true. They hit the ground simultaneously. This is one of those mind-bending truths of our universe, because gravity pulls equally on all objects, completely regardless of their mass. Now, as long as air resistance is low, so, we aren't comparing a rock to a fluffy feather just catching the wind, weight changes do absolutely nothing to affect falling speed.
Now, I know you're all totally eager to run outside and start measuring the world, but we need to have a quick, serious conversation first. Real scientists don't just care about getting accurate results. They also work safely. They prioritize safety above absolutely everything else, because, let's be real, dropping objects from high up places is inherently dangerous if you don't know exactly what you're doing.
So, if you're ever going to try a drop experiment, these mandatory safety steps are totally non-negotiable. First and foremost, clear the area below. You must ensure your drop zone has absolutely zero people, cars, or animals around. Second, avoid strong winds. They'll just blow your object right off course. Third, always use a small stone, never a large heavy one. And finally, wear the right safety gear if you need it. Setting up a perfectly safe drop zone is the true mark of a responsible scientist.
So, the crucial point is, this awesome measuring tool isn't just for skyscrapers. Once you have your stopwatch, your little rock, and your equation, this superpower works anywhere you can safely drop an object. It literally turns the entire world into your own personal giant physics laboratory.
Check out this fun list of everyday uses. You could drop a pebble into a dark well, listen for the splash, and calculate exactly how deep the water is. Or you could estimate the height of a steep cliff on your next hiking trip. Sizing up a massive tree? Easy. Just safely drop something from the top. You can even figure out the clearance height of a bridge over a river, or calculate exactly how high a drone is flying just by releasing an object from it. The physics remains exactly the same every single time.
Let's move to and see how this builds. Because what's truly amazing about this simple little equation is that it doesn't stop at trees and bridges. Oh no, it connects you to literally centuries of scientific discovery. The exact same rules we just used for our tiny rock experiment, they actually scale all the way up to govern the macro astrophysics of our